Good afternoon, class. Today we're going to work with functions, and we're going to talk about two different types of functions. A linear function is what we're going to start with, and then we'll end with talking about nonlinear functions. Let's first define what a function is. A function is a relationship that pairs. So we're talking about ordered pairs here, and we've worked with ordered pairs. X comma y is considered an ordered pair. We put numbers in. And a function takes an input value and assigns it to exactly one output value. So when we're working with input and output, we're going to define the input to be the independent variable and the output to be the dependent variable. So often we're going to deal with variables such as x that we're going to call the independent variable, and y is going to be called the output or the dependent variable. So when we're dealing with x's and y's, we're going to assign them to be independent and dependent. So what we want to do is go through these three examples here and see if we can determine which ones are functions and which ones are not. So we're looking for input values to be assigned to exactly one output. So 1 is assigned to 2, 3 is assigned to 4, -2 is to -1, and -5 is assigned to 4. So these x values are our input, these y values are the output, and exactly one output goes to each input. So this is a function. So we'll label this one a function. Here, 1 is being assigned to 2 outputs. So this is not a function because we don't even have to look at the other, even though 4 also breaks the rule. So this one is not a function because there are 2 outputs. We want 1 output. -1 is assigned to 1 for this one, -2 to 2, 1 to 1, and 2 is assigned to 2. This one is a function because each input is assigned to 1 output. Now we do notice here that there are multiple inputs being assigned to the same output, but the rule does not say anything about multiple inputs. It just says you can't have multiple outputs. So we have 1 output for each input. So this one's a function. So let's look at an example here where we have a diagram that creates a pattern, and we're going to see if we can decide what the pattern is and then determine if there's a function to it. So we're going to define the variables. X is going to be the triangles or number of triangles in the problem. We can see that there's 1 triangle here, 2 here, 3, 4, and so on. So creating a table here, we can see that the x would represent the number of triangles. Y in this relationship, based on our description up here, it's the relationship is between the number of triangles and the perimeter. We're going to let y be the perimeter. Now, review, perimeter just means the sum of the sides of the outside of the figure. So in this case, we're going to go 3, 3, and 4. The perimeter is going to be 10 because we add them all up. Then we're going to add this one up. We get 3, 4, 3, and 4. So this is going to be 14. Here we're going to go 3, 4, 3, 4, and 4 for the third triangle. So that one is going to be 18. We get 3, 4, 4, 3, 4, 4. This one's going to be 22. So it looks like, based on our pattern here, we're adding 4 each time we add a triangle. So we're going to complete the model here. The perimeter is blank times the number of triangles plus what? So if we take the pattern here as it is, we would say that the perimeter is 4 times the number of triangles plus 6. If we look at our pattern here, if we multiply 1 by 4, we get 4 plus 6. Then we multiply 2 times 4, we get 8 plus 6 is 14. 3 times 4 is 12. Plus 6 is 18, and we can see that that's happening up here because if we notice, the first triangle is taking the 4 here times 1, because there's 1 triangle, plus the 6 here. Here we're going to get 4 times 2. There's 2 4s plus 6. Here we have 3 4s plus 6, 4 4s plus 6. So our pattern does fit. So we would have an equation, and we would label it to be y, because that's going to be our dependent variable. 4 times x plus 6. So that's going to be our equation. Y equals 4x plus 6. So we use the table to list the points. So we would get 110. We would graph that. 110 is going to be right about in here. Then we get 214. 214 is going to be right about in there. 318. 18 is going to be right here. Getting off just a little bit, but it should work out. And then what do we add? Whoops, I was off. That's why. 3 is 18. So I'll erase this one. I apologize. I just had put the point in the wrong spot. And then 4 is 22. So we can see that this creates a line. So this would be a linear function because it creates a line. So let's look at representing a linear function from a table that's already been generated. So we're going to describe the pattern as it is in this description right here. And we can see that the x values here go from 0, 1, 2, and 3. So we can see that the y values are going up by 2's. So we may have something going on with 2 here. If they're going up by 2's, we may be able to determine what's going on here. We can also see that there's a pattern here between x and y. So I would say if we were, well, I always start with adding. So if we add 8, we get 8. If we add 8 to 1, we get 9. So adding just 8 is not going to be the pattern. So let's see if we can multiply. Let's see if we multiply by 2. So times 2, we get 0 plus 8. And then multiply by 2, we get 2 plus 8, we get 10. Times 2, we get 4 plus 8, we get 12. Times 2, we get 6. So it looks like, based on our pattern, if we times by 2, times the x by 2, and then add 8, we'll get our y value. So I'm just going to describe the pattern as times 2 plus 8. So x times 2 plus 8. So look down here at the choices. It looks like A is going to be our pattern. 2 times. And some of these just take trial and error. You might not get it the first time, but as you get through the patterns, you'll get better at it. So does the set of ordered pairs here represent a pattern? I'm going to leave the graphing for yourself to graph those ordered pairs and see if that one's linear. But what I'd like to do is get down here to this pattern here, and we want to see if this one is. So if we graph these, we get 0 for x, y is 2, 1 for x, 4 for y, 3 and 5, and then 1 and 8. Well, we can see that this, if we connect these, it does not create a line. So this is not a linear function. It's not even a function, because if we look at this, 1 is being assigned to 2 values. So this is not a function, let alone a linear function. So it's not a function or not a linear function. So those are some examples about linear functions and how you create patterns. You'll do some examples in class. Now let's talk about nonlinear patterns and functions. Something that's not linear is not going to create a straight line. Hopefully that's obvious to you. So let's look at some examples. Down here we have, so we want to circle each graph of a nonlinear function. So this one is obviously linear. It's creating a line. Here's a nonlinear. Here's a nonlinear. And this one's creating a line. So anything that creates a curve. So let's look at the table here and see if we can, let's see, create the pattern and see if we can figure out or recognize an equation that represents this. So we're going to look at the number of cuts in a triangle. So if we take the table below, shows the fraction A of the original area of a piece of paper that remains after the paper has been cut in half n times. So think about having a paper and folding it or cutting it, and we're going to see if this function is linear or nonlinear. So if we make one cut, it cuts the paper in half. If we make two cuts, that now has created a quarter of the area because we've cut this in half to get a quarter. 3 cuts gives us 1/8 the original area because we're taking a quarter and cutting it in half. And then 4 cuts is 1/16. So our ordered pairs are just going to be these numbers here. So 1 1/2, 2 1/4, 3 1/8, and then 4 1/16. So we can graph these 1 1/2, 2 1/4, 3 1/8, 4 1/16. We can see that this one 1/16 should be up just a little bit. I'm sliding in a little bit. So it looks like this is going to create, almost looks linear, but I can't quite, if I draw a line connecting these, it looks like they're going to not connect. These first 3 do, but this last one here rises a little bit. So it looks like maybe this one is going to be curving just a little bit if we connect it. It's tough to see by the eye, but I would say that this is not linear because it's curving. So let's move on to another example and see if we can determine what this is looking like. So let's look at another pattern. This pattern here is created by taking the branches, and we're going to add 3 branches each time. So the first one here has 3 branches on it. The second one will have 3 more branches on each one for a total of 9 branches off the end. So 3, 6, 9 branches off the end. And then this third figure here shows 3 branches off of the end of each one. So the number of new branches will be 27. And then we're going to continue. We're going to have 4. So we end up with, if we count those out, each one here is going to get 3 more. That's going to be 81, and I'll leave that for you to count out. It takes a while to count that. I'll show you the pattern in just a moment, how I'm getting the answer so easily. This would be 243. So you might ask, did I actually count out 243? No, I noticed that there was a pattern here. I noticed that these numbers here, 3, 9, 27, have to all do with 3 and what we're doing to it. So 3 raised to the 1 power is 3. 3 raised to the second power is 9. 3 raised to the third power is 27. So I just recognized that these were all just some multiple of 3. So I just took the number of branches to get the number of branches and just took which figure I was on and raised it to that. So this would be 3 to the 4th, 3 to the 5th. So it appears that the number of branches that we're going to get, the number of new branches, I should say, new branches is going to be 3 raised to the number of figures, or whichever figure. So the pattern in this case is going to be represented by y equals 3 to the x. So again, I went through that quite fast, but the idea here is to recognize the pattern and then write an equation for it. So let's do one last one here. We're going to write a rule for the figure, or for the function represented by the ordered pairs. So we have 1 and 1, we have 2 and 4, then we have 3 and 9, 4 and 16, 5 and 25. So just looking at these numbers, I can see that a pattern already is created, because if I take 1 and square it, I get 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. So if I just write my equation as y is going to be represented by taking whatever x is and squaring it. There's your equation or rule for the ordered pairs. So we'll do some more in class. Obviously, if you have questions on these, please bring them to class and we will discuss them.